Same base material and same fiber concentration. But this one is reinforced with Kevlar, glass and carbon fibers. So what do you think? Which one is actually the strongest? Hello, welcome to my tech farm. I have here 3 fiber reinforced ASA filaments by Spectrum. And I bought these 3 filaments myself, partly from the budget which I got from the polymaker, who is also a channel sponsor, and partly from the Patreon donations. So huge thanks to all my supporters, because together with the polymaker, they make this kind of videos possible. This is ASA Kevlar reinforced with aramid fibers, ASA-X CF10 reinforced with carbon fibers, and ASA-X GF10 reinforced with glass fibers. And in all 3 cases, the content of the fibers is 10%. And to be honest, I'm not directly so interested in the mechanical properties of this filament, but more about their properties compared to each other. So this is the main goal of this video. Overall, why do we need the fibers in the ASA filament? Well, first of all, the material will be stiffer. This means resist better to the bending, more temperature resistant objects, and less shrinking. This means better dimensional accuracy. But usually it will make the layer adhesion a little bit weaker, and it is more brittle, the filament itself. So if we bend it, it may break, but also the printed object is more brittle too. But as I mentioned, it will be tested in this video. About the prices, I can see these filaments are available in the USA too, but I can see only the price in euros, so this is used for the comparison. CF and GF, 54.9 euros for 1 kilogram spools. About the Kevlar, it is 46.9 but 0.75 kilogram spool. And we will see when I unbox it, but I have the feeling that these 1 kilogram spools are very full. And sometimes it may be a problem because they may fall down from the spool, because the density of the ASA is significantly lighter compared to the PLA or PETG. And if we use the same size spool, then it will be more meters, longer filament on that spool. Few specifications, the difference I could collect from their website. GF glass fiber, it breaks with smaller deformation, suddenly, no warnings before the break. Recently I tested ABS Kevlar, and there I experienced better layer adhesion compared to the no fiber reinforced ABS. We will see if that's the case with the ASA too. And also it is the most impact resistant material between these 3. Tensile strength, the carbon fiber reinforcement should be the strongest, then glass, and the end Kevlar or aramid fibers. And the carbon fiber reinforcement will result the most heat resistant material too. About the print settings, on the main pages they have the same numbers, for example for the nozzle temperature, which is between 240 and 270 degrees Celsius for all 3 materials. But on the comparison page and on the numbers given on the box, it's a little bit different. For example, on carbon fibers we have just a little bit lower nozzle temperature. Let's start with the unboxing. The Kevlar packaging is a little bit different. Vacuum packaging in all 3 cases, but only the Kevlar have this better material for the packaging. And these are half kilogram spools. This is good because the spool is not so full. This is ABS Medical, also from the Spectrum 1 kilogram spool, and see how full is it. And this is sometimes a problem. For example, it cannot even go into the AMS unit. But let's see how brittle are these filaments. All 3 bags are resealable. Kevlar, and this 0.75 kilogram spool looks quite full. This is carbon fiber and glass fiber version, these 2 in natural color. Let's see how brittle is the filament. Kevlar, not too brittle. Start angle 22 degrees. And it's not even broken. Carbon fiber version. Oh, this is more brittle. Start angle also 22 degrees. Oh, around 60. Definitely very brittle material. And the glass fiber version. Somewhere between. Let's measure it. Start angle also 22 degrees. It was broken somewhere around 100, so definitely less brittle than carbon fiber version, but more compared to the Kevlar. The carbon fiber version is very brittle material and it may break inside some printers, for example inside H2S, which bends that Teflon tube quite a lot. Each will get 4 hours of drying on 70 degrees Celsius, and then I will start the printing, and I'm starting with the carbon fiber version. My regular test objects. The start profile Bamblab ASA CF, but let's see the modifications. 60 chamber temperature, on the bed 100 degrees Celsius, nozzle 270 as the maximum recommended for all three materials, the maximum flow 12, the part calling, the minimum I'm reducing from 10 to 0, so only on some overhangs it will use 25 as a max, which is still quite low. Start of the printing is good, and I know it will be fine, only I'm hoping it is not too fast, and you will see a decent layer adhesion. Wow, broken filament. Yes, the brittle one. I was just pushing in the filament and it already broke. New record, this is one of the most brittle filaments I ever tested. Just a little bending and it's already broken. Printing on good old X1 carbon, where I also never had a filament break before. Looks like I have new filament for my future 3D printer testing. I'm using the same settings, only I don't have actively heated chamber here. And I'm very curious how will this printer work with these brittle filaments. And look at that, it will be finished soon. X1 carbon, it can handle very brittle filaments too. Pity that this is discontinued printer. The temperature inside chamber stabilizes around 50 degrees Celsius. Bed adhesion is great until it's hot. Yeah, I have to wait until it cools down. And I decided to print all test objects on the X1 carbon for the better comparison. A few more objects for additional testing. Same file, same printer. This is from glass fiber version. I'm using exactly the same settings for all three printings. Same test objects from ASA Kevlar. And the last group with the Kevlar fibers. Let's measure the shrinking. This is Kevlar. And I noticed some elephant foot, so I'm measuring above it. 79.60. This is basically very similar to the average ABS or ASA without fibers. This is glass fiber version. 79.71, so less shrinking with this one. And the carbon fiber version. 79.92, so the smallest shrinking with the carbon fibers. Tensile test, this is Kevlar. These are horizontally printed objects. Glass fiber version. Stronger a little bit. And carbon fiber version. The strongest from these three. And here you can see the numbers on the graph. And with this line I marked the average ASA without any fibers. And we can see the CF is a little bit above it and the other two below this line. Layer adhesion, Kevlar. These objects are printed in vertical position. Glass fiber version. Stronger a little bit. Carbon fiber version. This is also very weak. According to my rating, the Kevlar and carbon fiber version are quite weak, the glass fiber acceptable, but in all three cases they are far below this line average ASA, of course without fibers. Shear test, objects printed in horizontal position, side by side all three materials, and these are printed in vertical position. Here the layer adhesion is important. When printed in horizontal position, the fibers always helps a lot, but only carbon fiber version is stronger compared to the average ASA without any fibers. The Kevlar and glass fibers are below this line. Printed in vertical position, the layer adhesion is important here, but interesting in all three, actually in all four cases, these are very similar numbers, and more or less quite weak compared to other filament types. Torsion test. Objects printed in horizontal position, loaded 90-degree rotation, and this is the maximal load, 1.2. These objects are printed in vertical position, and this is the maximal or breaking load. Interesting that in horizontal position, carbon fiber was the strongest. Printed vertically, well, I was expecting more from these filaments. Printed in horizontal position, this is the first test where the Kevlar version was the strongest compared to other two, but even that is weaker than average no-fiber ASA. When printed in vertical position, in all three cases they are weaker than average ASA, especially the carbon fiber version. Grip as a deformation under constant load, ASA Kevlar, glass fibers, carbon fibers. The load is 1.25 kilograms. Visually smallest deformation on carbon fiber, 17.46, 15.40, 12.77. So this is their initial deformation, and now let's see the last measuring. Day 5 time for the last measuring, but even now I can see the biggest deformation on Kevlar, then glass and carbon fibers. 18.68, 16.00, 12.86. Let's remove the loads. Very small permanent deformation, but still the biggest one is on the Kevlar. On this graph we can see the distance between two reference surfaces, and we can see biggest deformation on the Kevlar version and far the smallest on the carbon fiber version. But the creeping is the difference between 2 days, and that's presented on the second graph, and we can see quite big initial creeping on the Kevlar version and far the smallest on the carbon fiber version. Even on the day 1 it is very minimal. Temperature test in the oven. When I'm about to record the temperature of the first noticeable deformation, M10 not as a small load, and the first one which started with deformation was the Kevlar, then glass fiber, and the last one the carbon fiber version. At 130 degrees I stopped the experiment, and I just wanted to check how hard or soft they are. Carbon fiber version quite hard, but these two are very soft. It is typical that the fibers increase the temperature resistance, but in this case only with the carbon fiber version. The other two, Kevlar and glass fiber, they have similar temperature resistance like no fiber ASA. 3-point bending test. Distance between supports is 50 mm, and these loads are placed one by one, and I am recording the deformation after 1, 30 and 60 seconds. And currently you can see the deformation under 10 kilograms. The permanent deformation is very minimal on carbon and glass fibers. On Kevlar, during the test it had a huge deformation, but now the permanent deformation is visible but much smaller. In this case the carbon fiber version is quite strong, very minimal deformation, even under 10 kilograms. And the Kevlar, quite weak. Look at this big deformation under 10 kilograms during that 1 minute. And the glass fiber version is somewhere between. And then my second bending test on that universal testing machine. Distance between supports is 64 mm. And not only the maximal load, but also the behavior is different between these three materials. The machine stopped with the testing when it reached 50% from the maximum load, or after the break, like in the case of Kevlar. 3 graphs side by side. Maximal load, bending strength and elastic modulus. Well, if you watch the bending strength and elastic modulus, the carbon fiber version is the strongest, especially here. Very minimal deformation under maximal load. Impact test sharp is standard. And the results from 3 measurings. ISO's impact test. And again the results from 3 measurings. Looks like the Kevlar and the carbon fiber version have a very similar brittleness, and the toughest between these 3 is the glass fiber version. A simple hook test. The strength here is very similar and actually quite weak compared to other material types, because a weak layer adhesion will also result weak wall adhesion, and this is important in this test. Open-end wrench test starting with Kevlar 1.2, glass fiber version 1.1,
and carbon fiber version 1.5.
Box and wrench Kevlar.
Kevlar 2.4, glass fiber 2.1, carbon fiber 2.1. Our results one more time: creep test, tensile test, layer adhesion, shear test horizontal and vertical, bending the deformation under these loads after 30 seconds, bending the deformation under these loads after 1, 30 and 60 seconds, torsion test horizontal and vertical, impact test ISO and Sharpie, temperature test, that second bending test, and the hook test.
But the main aim of this video was to compare these three fibers to each other. I'm not sure how universal are these properties, but the strongest in most cases was the carbon fiber version. Resists the best to the bending, highest tensile strength, but this is very brittle, the filament itself. Just a little bit more bending and it will break in Teflon tube, and I'm quite sure that I would have problems on some printers like H2S, Creality K1 Max, GDQ2 and similar. The highest impact resistance, for example, was with the glass fiber version. About the Kevlar, there are some tests where it was the best, but the advantage was very minimal, and I'm not sure is there any other advantage of this fiber reinforcement type. I already tested the ABS and there it was basically quite weak, very similar properties like with the non-fiber reinforced ABS, or in this case ASA, but it is still very brittle, so it lost that advantage. Okay, so this was my experience with these filaments. Overall, compared to other average ASA, these are quite weak materials, especially because of the layer adhesion. Maybe I could play a little bit more with improving this property, but I was already printed on the highest recommended print temperature and I reduced the part cooling to 0. Only on some overhangs I left some percentage, so basically I think I maximized the recommended properties. If you have some other experience, show us down in the comment section. Thank you for watching this video until the end and, happy printing!